My name is John Parry and I'm a Business Development Manager for Siemens, responsible for the Simcenter Flotherm product line. My talk is about trends in simulation-based thermal design. Let's start by looking at key industry trends. Electronics has become the main source of value add and profit for other industries like automotive, with electric vehicles, driver assist systems, and now autonomous driving technologies. The electronics industry is arguably one of the most innovative when it comes to emerging technologies. 5G requires an entire ecosystem from network infrastructure players like Nokia and Ericsson to smartphone providers like Samsung, with significant rollout challenges. The digitalization potential arising from 5G performance, combined with artificial intelligence, virtual and augmented reality, is enormous, and we are just at the outset. With electronics going into everything from cars to home appliances, consumers want products that are more personalized. Manufacturers can increase the refresh cycle as products are replaced to get new features, not because they have worn out. In this highly competitive and increasingly personalized market, companies must take every opportunity to become leaner and more efficient to keep up the pace, starting with design. With globalization, electronic design, manufacturing, and market fulfillment are now happening across continental and company boundaries. More businesses are outsourcing manufacturing. As an example, Apple iPhones are designed in the US, built by Foxconn in China, and shipped around the world. 6 different handsets are currently available to purchase. Let's look at the consumer-driven trend in more detail. The desire for new functionality is clear, benefiting the suppliers that can deliver it, but consumers have other requirements. As we have seen with TVs, smartphones, tablets, and wearable devices, consumers want products that are both light and thin. Silent or very quiet operation is increasingly appreciated in both office and home settings. Despite products being ever more complex, consumers retain an expectation that the product will be robust and reliable. A smartphone should not break when dropped. A laptop should run for more than 4 years without becoming noisy. There is an appetite for new technology, as we see with queues outside Apple stores when a new iPhone is launched. To stay competitive, new technology has to be proven and new products designed and brought to market faster than ever before. These key trends are made possible by 2 technology drivers within the electronics industry. The first of these is Moore's Law. In 1965, Gordon Moore, the co-founder of Intel, observed that the number of transistors on a microchip doubles every 2 years, while the cost of doing so halves. The first part of that prediction has held true. Creating transistors at the next size or process node is no longer delivering the same cost reduction due to the huge increases in capital expenditure. With transistors now as small as 5 nanometers, breakthroughs that reduce cost are harder to achieve. While smaller transistors increase functionality in high-end products like smartphones, the electronics industry has sought other ways to reduce cost. Heterogeneous integration is sometimes referred to as more than more. Heterogeneous integration brings together several chips, each produced at the most cost-effective process node, into a single chip package. Miniaturization is achieved by stacking die within a package and by stacking packages together. So what are the implications of these 2 technology drivers? Both Moore's Law and heterogeneous integration build more functionality into a smaller space. Despite efforts to reduce power consumption per transistor, the power density, being the amount of power dissipated in a given volume, has increased over time. Higher power densities lead to the need for increased cooling. The market demand for thinner, lighter products has resulted in less space for cooling solutions and more restricted airflow through systems. The consequence is that a new product may run hotter than its predecessor. This has implications for consumers and ultimately the manufacturer. What then is the impact of hotter products? Firstly, heat degrades performance with the equipment running slower. This is particularly true of computing-intensive applications, including graphics processing. Operational issues also tend to increase as heat affects voltage and current tolerances, which can cause equipment to lock up or hang, returning to normal operation when the temperature drops, and in some cases after rebooting. More seriously, heat increases almost all of the damage mechanisms through which electronics products age and eventually wear out. So physical failures increase and lifetime is reduced. An example is cracking of solder balls. Finally, there are safety issues associated with the touch temperature of exposed surfaces of the equipment becoming too hot. This is a particular issue for metal surfaces and in applications where the equipment is designed to be hot swappable. In wearable devices, if the temperature exceeds just 40 degrees Celsius, a low temperature burn can arise. Using a laptop with a lithium-ion battery on a duvet that blocks the air vents underneath is undesirable. Let's consider the implications of increased cooling. Cooling solutions such as heat sinks, heat spreaders, and fans all add weight to a product. As the limits of air cooling are pushed, copper is being used instead of aluminium for heat sinks, and copper is more than 3 times heavier. Along the same lines, cooling solutions take up space, and space is also needed for the air in air-cooled products, which limits the achievable form factor. Fans increase power consumption, which can reduce battery life. Many electronic systems incorporate active thermal management, where the performance of the system is temporarily degraded, usually by reducing processor frequency, until temperatures are brought under control. Ultimately, the system may be halted if such strategies are unsuccessful. Laptop coolers are an aftermarket product intended to help consumers keep their laptops cool. Cooling solutions increase the product cost, directly due to the cost of the components used, and indirectly development costs increase due to the challenge of closing the thermal design. All of these run counter to the characteristics consumers want in a product. So what are the possibilities? What can be done to address the challenges posed by increasing heat? Electronics thermal design is complex and can only be addressed effectively with simulation. A simulation-driven approach to thermal design is essential. The good news is that a great deal can be learnt about the thermal performance of a new product at the concept stage before significant resources have been committed to the detail of the design. Within hours, different cooling approaches can be tried and the most viable approach chosen. Decisions made at the concept stage can make or break the thermal performance of the product. The electrical design often starts first and consumes significant amounts of time and resource. Communicating key aspects of the thermal design to the electrical design team ensures this main development activity can proceed most efficiently. Thermal design software sits at the interface between the mechanical and electrical design worlds. As data gets committed into these main design flows, the thermal model can be updated and run to check that the thermal performance is not impaired. As well as improving the product, simulation-driven thermal design provides business benefits to the organization. Keeping the thermal model in sync with the EDA and MCAD workflows ensures these main development activities progress smoothly. A simulation-driven approach reduces the number of engineering change orders due to thermal issues. Avoiding time-consuming rework activities shortens the development timescale considerably. Thermal engineers' time is freed up for innovation activities needed to meet the thermal performance challenges of future products. A final benefit of taking a simulation-driven design approach is that it eliminates PCB respins due to thermal issues post-design. This saves the time and cost required to redesign, remanufacture, and retest the board, which delay getting the product to market. Within the Simcenter portfolio, we have a number of solutions for electronics cooling challenges. The market-leading solution for this application is Simcenter Flotherm Flexx. Here are some typical applications for Simcenter Flotherm Flexx, which range from components all the way up to systems and even data centers. The Flexx license provides a single key that gives access to either Simcenter Flotherm or Simcenter Flotherm XT. Simcenter Flotherm Flexx supports the electronics supply chain with the ability to supply models as library items for other companies to use within their own models, for example, component models to go on boards. Simcenter Flotherm Flexx's unique set of capabilities allow it to be used at all packaging levels, from the ideation stage onwards, all the way through to the final design, when Simcenter Flotherm Flexx is capable of creating a true digital twin of the thermal performance. Let's briefly look at just 3 of the 40+ examples we have showing the value Simcenter Flotherm Flexx can deliver to customers. Our first example comes from Fujifilm. Using Simcenter Flotherm, Fujifilm build and revise thermal models of their cameras to define what parts and their size are needed to dissipate the heat. The optimal thermal structure then guides the CAD design, with CAD geometry imported and checked for thermal performance as soon as it becomes available. Accurate temperature prediction is needed to meet component specifications and a maximum touch temperature limit. Denso is another interesting case. Using Simcenter Flotherm, Denso have managed to compress their thermal verification cycles by 62% while achieving a 78% cost reduction in the thermal design of electronic control units. This is all the more remarkable given the number of different ECUs that Denso produce has exploded, with high-end cars now having more than 100 ECUs that are used in everything from driver assist systems to electric powertrain and beyond. A final example comes from NXP. Their customer wanted a 25-watt charger in the same housing as their current 18-watt charger, so a 26% increase in power. Thermal considerations drove every aspect of this development. A 50°C touch temperature limit meant that hotspots had to be eliminated. Capacitors had to be moved. The main power transistor was moved to the other side of the main board and away from the transformer. The size of a small second board was increased to increase heat spreading, and ultimately the power pins and the USB cable all play a part in the cooling. By taking a simulation-driven design approach, NXP were able to avoid having to use more expensive components. To recap, simulation-driven thermal design is needed from the concept stage to choose the right cooling approach and optimize that for cost and performance across the product development. Done correctly, the consumer demand for innovative products that are light, thin, silent and reliable can be met. Design rework due to thermal issues in both the main mechanical and electrical design flows can be eliminated, saving time and significant development resources. First physical prototypes pass thermal verification, so engineering time can be devoted to innovation, not fixing problems found in late design or prototyping.